So in this problem, we are asked to find the mass of the rocket as a function of time if it moves with a constant acceleration alpha in the absence of external forces. The gas escapes with a constant velocity u relative to the rocket and given its initial mass as m naught. And it's told in this example that external force is 0. Let us put the equation again. We got F plus F external force plus thrust due to that ejected mass. We have it as V relative dm by dt plus that's equal to m times dv by dt. M is mass of the system. In this example, external force is set to be 0 and the relative velocity is u. And the ejected mass, as we know that it should provide some encouraging thrust. So acceleration should be there. So acceleration means it should be positive. But the m of the system is decreasing. So for having the acceleration positive, I am taking, instead of writing dm by dt, I am putting minus dm by dt because dm is negative and m is decreasing. Let's rearrange things. We would have, it's told that acceleration is alpha. So u dm by m and alpha dt, taking integral on both sides. Initial mass is m naught. Let's say the final mass is some m. All this happened in some interval t. So minus u ln m by m naught equal to alpha times t. We can write further as m equal to m naught e power minus alpha t by u. So this is the mass of the rocket as a function of time t. Let's look into the other problem. We are asked to determine the force F. That F is shown in the diagram. Required to give the open link chain a constant velocity v. The chain has a total length L. Mass per unit length is lambda. Neglect the small size and mass of the pulley and any friction in the pulley. I have to maintain this force F so that I pull this chain with uniform velocity v. See, for having uniform velocity as net force should be 0, the force, I need to do two things here. The adding dm onto the right side as I pull the chain, as mass is added, it provides a discouraging thrust for motion of this chain to the right. And the other is the unbalanced weight of the chain on the both sides. So the force that is required, F required to be applied, equal to, you can see on the other side this extent mass is hanging on the right side so as to maintain uniform velocity. Firstly, I have to apply this unbalanced force. The unbalanced force is h minus y is the excess part on the left side compared to right side into mass per unit length. This gives me the mass of that unbalanced portion into g. So this is the unbalanced gravitational force. This I have to maintain. Otherwise, if I don't apply this force, the chain should definitely fall to the left. Along with this, as I am pulling the chain, the adding mass develops some thrust. The thrust developed by the adding mass is, this thrust also I should be balancing, because this thrust won't be encouraging, it would be uh, opposing the motion of this hanging mass. So that means the thrust that is developed due to the hanging portion is acting this way. So my force which is downward, so as to balance this thrust, I should add this on the right side in the equation. That will be given by V relative dm by dt. V relative dm by dt. So dm by dt is on the right side, what I have is uh, lambda y. So I think I would have uh, h minus y lambda g plus, this is v, which is the speed of the chain, and lambda I can write outside dy by dt, but you know that dy by dt is again v. So therefore we can conclude F required is equal to h minus y lambda g plus lambda v square. So this is the force just required to pull this hanging part down with a constant velocity v, where v is dy by dt. Here we got another example. A chain of mass m and length L is held vertical such that its lower end just touches the floor. It is released from rest. So find the force exerted by the chain on the table when the upper end is about to hit the floor. So let us make some diagram visualizing that hanging chain. This is a full chain hanging. So the length of the chain is, say, L. It's a uniform chain. Mass of the chain is given as m. Now let's say, if suppose at some instant you got a negligible heap formed here. Let's say that y is the length of the chain above the table. So during the fall, you can see this, when y is there, that means the extent the chain moved, any part of the chain moved, any point of the chain moved is L minus y. So at this instant, velocity can be v, velocity of any particle of chain can be d by dt of L minus y, and that would give me minus dy by dt. So what force does chain exert when all the chain fall? Suppose if entire chain is simply resting on the table, definitely it should be mg. But not only that, in the last instant when that elemental mass that is adding to that heap, you'll be of course neglecting the heap in this case, that provides some thrust. So let us see what is that. So here F by chain on table would be its weight. Along with weight, that thrust is required. So the thrust is, we can write it as V relative dm by dt. So we can write F required, or F is equal to mg plus V relative at the moment just before it strikes that is root 2gl, and dm by dt is d by dt of lambda times that hanging length. So that hanging length at any instant we wrote it as L minus 5. So we can write M, of course I'll show this as V here, lambda minus dy by dt. You know that minus dy by dt is V. So we can write mg plus lambda v square. But we know that V acquired by falling under the influence of gravity, every particle is falling under the influence of gravity through L is given by root 2gl when all the chain fall. So mg plus lambda L into V square is 2gl. Lambda into L gives me m. So I can write it as mg plus 2 times mg. Therefore, F on table will be 3 mg. 3 mg is the answer.